Okay, recording. And let's start the broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Hey, welcome you guys. This is Ryan Dio from Typhoon HIL. I'm an applications engineer, and I'm here with Albert Dunford from PowerSim.
Hi folks, Albert Dunford here from PowerSim. And Ryan, take it away.
Sure. So today we're going to be talking about rapid control prototyping. And we've done something similar to this in the past, but we kind of feel like we needed to dive into way more details. So what we're going to do today is kind of do a very in-depth tutorial on rapid control prototyping, kind of going over the process and also kind of showing you hands-on how to build this from the ground up. So we'll kind of start off with some slides and we'll show you the agenda kind of as a start. So we'll start with intro, did that. We're going to give you guys a really good tutorial on the actual process of rapid control prototyping and what it is. And after we do that, we can kind of do some questions if you guys have them, and then we can move into a more of a demo style format where we can do some things like offline simulation, code generation, and controls testing, and then we can move back into Q&A. If you guys have questions throughout this entire webinar, please feel free to ask them. There's a little questions drop down in the GoToWebinar application, so just use that and feel free to ask questions at any time.
Yeah, so just to give you kind of a time frame here, we have booked up 90 minutes. Ryan is recording and we'll post it on our corresponding website so you can watch the recording afterwards. But yeah, I think we're anticipating maybe 20 minutes on slides, 15, 20 minutes on slides, and then as much time as possible, really just kind of diving into the actual doing the process from start to finish. And yeah, as I said, hit the questions there. If you feel your question is really long, I think there's a method of raising your hand, and then we can unmute you so that you can ask your question verbally if needed.
Cool.
Ryan?
So
it looks like Chris has joined in now.
Awesome. We also have Chris Clearman with us from Texas Instruments. You can kind of help out answering questions regarding the TI MCUs that we'll be using. So let's get started with the kind of what RCP is, why you should do it, and kind of what benefits it would provide. So testing in general for embedded software development is something that may be kind of straightforward for a lot of people, but not so much for others. Generally, the sooner you can start testing software, especially in the embedded realm, the better. It provides insights like finding bugs early in their development versus later. It minimizes your costs, therefore you can decrease your development times and you greatly minimize your risk. So as you the sooner you test, the better off you're going to be. And there's a lot of ways you can kind of do these different types of testing. Each kind of has its own benefits, and we'll kind of walk into those a little bit more. So we have a typical process here for embedded software development. This may look pretty familiar to some of you guys. This kind of follows a model of verification and validation, where we start with the design. You move to prototyping. So the design would be, say, in an offline simulator. The prototyping of your code would be on a prototype hardware platform. So in this case, we're actually going to be using a TI development platform, and that's where you'll basically be testing your code in that spot. You'll be generating the code onto that Texas Instruments platform in this case, and then you validate those results using various testing methods. For this one, we're going to use HIL. And then after you do all those steps, you basically do physical testing last. That's with the real hardware controller once you kind of have that controller ready. So this kind of enables you to do your software testing before you actually have the physical hardware even in your hands. So you can test your code and make sure that it's robust before you even put it on to your real embedded platform. So what is RCP? Basically, it's the allowing of tuning of control algorithms, and it allows you a quick way to test and iterate your control software. Typically, this involves some type of code generation and hardware in the loop test. And if you jump back a slide, actually, you'll see that these four first things here, everything except for physical test, that's actually going to be what RCP is. I mean, RCP will involve designing, taking that prototype hardware and code generating to it, and then validating that with HIL. But what we're going to do is do this kind of multiple times in small iterations. That way, every single component that we design, we can test, kind of like in a unit test style fashion. So testing small bits and then adding more and more and testing every single small piece. And this is going to be on a prototype platform, which would be a similar processor to our real physical board. So after this is done, we can basically port that to the real controller once that's ready, and your code should be very, very robust and ready to go. Yeah, so why RCP? I kind of talked about this earlier, but the sooner you test, you're going to reduce your risk, you'll decrease the cost of development, and you'll decrease your development timelines. Just by doing this process, it really speeds things up, makes things more affordable, and greatly reduces your risk. And there's a lot of, I guess, different RCP platforms out there. All of them kind of have different benefits and provide different things. Not all of them have code generation, for example. Not all of them use hardware in the loop tests for validation. But generally, the best ones should provide a way to import and design control and then seamlessly generate code to a prototype controller, like I mentioned earlier. The prototype controller should be of the same processor family and should be very similar to your end development board, which you'll be using. And it should be interfaced to a real-time PC or simulator via real physical inputs and outputs. You don't want to make any modifications to your controller when you're doing this testing, just so that you know that everything is going to be working perfectly once you move it to the real hardware. The real-time simulator should be capable of simulating these plant models, which will be interfaced to the controller. And this needs to be at a fidelity where basically the controller can't tell the difference between the plant model and the real physical system. So you need a really fast simulation step time here, and you need to have a very good plant model. And your RCP platform finally should be able to continually test and iterate your control software with that code gen. So these are kind of like the best things that we know of that enable the best RCP platforms. So that's kind of what you should look for whenever you're looking for these platforms. So today we're going to have this set up here. We'll have the complete system simulation in PSIM, and we'll be doing a couple of different models here where we can show you guys some open loop and closed loop, and Albert will be able to talk on those some more. We'll do some automatic code generation, also using the PSIM sim coder. We're going to basically be taking this, these simulations and generating code down onto that TI embedded processor, the TI F28335. This card is going to be hooked up onto a TI DSP interface board provided by Typhoon HIL. And this is just mapping the analog and digital channels to the hardware in the loop unit. So the hardware in the loop unit used in this demo will actually be the Typhoon HIL 600, not the 604. The 604 is just the latest and greatest simulator that we have, and it's really cool to show off. So that's why I put it there. But what we'll be doing with this controller is generating the code to it, and then the code will be running on that embedded processor, and then the hardware loop unit will be simulating kind of the power stage, and it will basically trick the controller to think that it's plugged into the real thing. So that's today's setup, and we can kind of show you this in some more detail now, I guess.
Yeah, yeah. So the simulations I've got set up here, we're going to go through open loop with no cogeneration elements. Then we're going to go open loop with cogen and run the inverter setup that we have with the inverter hardware loop in real time with the code that we generated. And then we're going to do a little bit of, I'm not going to spend a lot of time diving into the control design. I'll show you how the control design is done with PSIM and then with another tool called Smart Control, how those the PI coefficients are determined. And then we're going to go straight into code loop, closed loop cogeneration and verify this with the HIL system, and then we'll get into some simple protections that we've implemented, and we'll hopefully we'll have enough time for all this stuff, and then leave some time for questions. But if there's any questions right now, now would be a good time to ask.
One thing I think we forgot to mention is we'll be putting a pretty thorough tutorial guide up with all these examples and kind of a walkthrough, and you can expect to see that up probably in the next week or two, and that will be probably when the recording goes up.
Yeah, and on that subject, this is going to be the first of a series of webinars that we're putting together. So this one, again, just on a simple inverter, but three-phase inverter. But we're going to be doing, getting into GridLink, PV inverter, microgrid type style simulations, getting into motor controls, and getting into some more complex simulations a little bit later on. Definitely. This one is really just an intro into how the process works and to familiarize you with the tools with a somewhat easy but not too hard example, so that the upcoming webinars as they're released, will hopefully build on what happens here to really show the power of the system. And there's no questions so far, so I'll take it away into the simulation stuff.
Yeah, that sounds great.
Okay. Discard, minimize. Okay. So I've got first off, I'm going to, here's our little open loop simulation, but I'm going to show you turn on my webcam and show you what is going on here and with regards to hardware. I've got an F28335 processor, and then this is going to plug into the control card right here. So this is the control card for the Typhoon HIL unit, and this is one of the older, I think they have a new flashier red one now. So yep. This accepts any TI control card, and so this slots in, and then all of the analog, the digital input and output pins are mapped to this header, and then this header has all of the analog inputs and outputs are mapped from the processor, and so there's test points. So we'll probe some test points here as well, and so that you can see some of the signals that are coming in and out between the HIL unit and the processor. I've got a little USB oscilloscope here called a picoscope with some test probes, so we'll be able to probe signals. This is the HIL unit itself. I won't pick it up. It's underneath my laptop stand here, so that's going to be a little bit difficult to show you, but there's the HIL unit there, and so this just slots in at the front like so. I have a JTAG connection to flash the DSP. So this is the XDS 100 version 2, and so this just slots in, and this is how we'll be uploading the code to the DSP. And what else can I mention here? I've also got
a using the standard TI Uniflash, correct?
Yeah, it's the basic. I use the basic CCS, the latest version of CCS, the free version, and that's that'll be what I'm using to compile the .out file. I always thought RCP is connecting a real-time simulation. There's a question that's come in from the ECU and the real plan, or so we're going to be generating the code. So it's a good question. We're going to be generating the code and running the code in real time, and then verifying the operation with a real-time hardware and loop simulation, which what the HIL block is doing. So it's a full process that we're coming through. So yes, we're doing a real-time verification of the control code on the DSP against a hardware and loop simulation, and then as we close loops and start testing the code, we'll come back to PSIM and gen new code and make rapid decisions and changes to the control code.
It's all about iterations.
Yeah. Okay. So the first simulation we have here, I'll run it quickly. This is just a really simple open loop simulation. We've got a 3-phase inverter, and all I'm doing is driving it with, I didn't change the load on this one, 5 milli and 5 milli. So this one is really simple. Just a real simple 3-phase inverter. We're driving 3 sinusoidal sources offset by 120 degrees into a carrier waveform generation, and those are driving the switches there. So there's not really too much going on in this particular simulation, and so I'm going to shut this guy down, and we'll move to the next simulation here. This simulation is now a setup for code generation. In the previous simulation, we took control signals driving into a comparator waveform with carrier waveforms, and that has been now replaced by a control block here that is for the F28335, and this is initializing or controlling the 3 PWMs that we're going to use, PWM timers 1, 2, and 3, and we've also defined our carrier waveform here as a triangular waveform with, and we're going to trigger the ADC, and we've got a carrier waveform defined as 2 peak to peak of 2, so -1 to 1, and that's what this is doing here. Yeah, essentially what we've also got set up is an ADC block, so we can look at the ADC signals that we map in, and I've also got here, let me just move this back a little bit so you can, we'll keep an eye on what's going on here in a moment here. So this block sets up the analog to digital conversion process, and we've also got some elements here to help us with tuning, scaling, and offsetting the feedback values properly. So we can run this simulation, and this one is going to give us essentially the same results as that other simulation. So nice 3-phase sinusoidal waveforms. We're controlling this now with DQ control. So we've got a ID and IQ reference, and we've got a frequency generation here. So we're running at 60 hertz, and we can look at the waveforms again, nice smooth 3-phase waveforms. So what we'll do actually is generate the code for this and flash the MCU and run this guy in MC loop to make sure that everything is working okay. So to generate the code, we go simulate and then go to generate code. This is the C file that gets generated. So there's a couple things to notice here. We've declared an interrupt routine called task, and task down here is declared, and task, we can see that we're fetching values from the ADC. We are doing a DQ transformation right here, and so every variable, FDQ1 or sum1 or multiply 1, 0 to hold 6, these are all the names of these elements here. So DQ01 is this element, or these lines of code right here, where we're going from DQ to ABC. What is the trip zone defined in the 3-phase PWM? The trip zone in the PWM is defined as we're not using it. So we're disabled all the trip zones right now. So we're not using the trip zones in this instance. We could set that up, and we'll play with the trip zones later on. But right now, the trip zones are not defined, or they're not in use. So this block, and we'll look at the how this is all set up down at the bottom here. So the main thing of what PSIM is doing is it's generating all the peripheral function setups for us. So we're just defining timers, we're defining how to use the three-phase PWM, and we're defining how to define and sample the ADC. So these are all handled here, and then we go into this infinite for loop, and we just basically, we're waiting for that interrupt routine to pop so that we can do the control, the open loop control. So, so this is the .c file. Really what's been imported into or been generated by PSIM is three-phase, this one here. So this is the same file that we're just looking at here, so three-phase inverter with open loop code and SCI comms, and we've generated an entire CCS project. So to bring this into, so we've got linker, library files, header files as needed. So all we need to do is import this project file into CodeComposer Studio, which we'll do right now.
At what point would you suggest, Albert, that people move from, say, offline simulation to code gen? Would you say that's a pretty quick thing that you would, or a quick step you'd move from?
Yeah, it's really quite quick. So again, in this instance, we can simulate this still. So the only real disadvantage is these code generation elements slow the simulation down a little bit. So we can run a simulation that has code generation elements in it all the way from the very open loop stages to the fully defined closed loop. There's one set of simulations where we need to have that we need to run without closed loop, and we'll get to that in a moment here when we define the controller coefficients.
Cool.
So as importing the project is just as simple as going into import legacy project, and then we browse to that particular file location, which is buried a little bit. So we'll grab this project file, we'll click open, next, and then we'll hit finish, and it imports that project for us. And there's always a couple warnings. I think it has to do with XDIAS. I'll leave Chris to answer questions about why XDIAS isn't included anymore. And here is the C code. So the next thing I'm going to define, which is quite important, is my communications to the processor. So I've defined a target configuration over here. So this target configuration is toggled from the target configurations menu. And what this is, if we double click on this real quick and see what it is this is, I'm connecting to the F28335, I'm connecting over debug, and we can test the connection, and we should get a successful test. So now that's talking to the processor, and if you scroll down, we should see succeeded. So we should be good to go. So we'll close that. We'll minimize that. Okay, so we can see I've got a timestamp here. I'm actually connecting here from the West Coast, so I'm on Pacific time right now, so 12:19:18. And whenever we generate code again, simulate, generate code, we've got a new timestamp. And now that we've imported the project, the code automatically updates. So we don't need to go through that importation process multiple times. We just need to regenerate the code again.
Yep.
So let's fire up the Typhoon HIL side of things. I think I closed down my control center. So what we'll do is I can actually start this running while we're waiting for the Typhoon to start running. So I'm starting debug right now, and I'm starting this to, and as the project is building, we're loading that .out file, and the processor is automatically going to start in the pause state, and we'll be able to look at the PWMs in a moment here. So we'll just run this. Again, we're running an open loop, so we're going to have PWMs on here, and I'll probe. So this is my my probe window here, and I'm going to use my probes my probes, and I'm going to grab the phase A complements or pairs here. So we'll go down, we'll set up a trigger. So we've got our complementary pairs here going away, and we can see we're getting the sinusoidal PWM pattern, so expanding and contracting duty cycle. And I can stop this, and if we zoom in on this now, we can see that we've got some dead time. The dead time defined is 500 nanoseconds. So if we come back to the this block here and double click here, we can see that that's what our dead time was defined. So if we want to change the dead time, say put in like 1 microsecond, hit OK, simulate, generate the code again. We've got a new timestamp. So we can come back over to CCS, we can pause and stop this, and we can see that that new code is automatically loaded in with the same timestamp. We can start debugging again. And we'll hit play, and then back over here, if we start this running again and stop, we can see we've got a new, the new dead time of 1 microsecond. So really easy to go and make changes, generate the code again, and close the loop that way quite quickly. So looks like Typhoon is launched up, and we'll load in an inverter to play with.
So this will basically just be simulating the plant,
yeah,
which will be the inverter in this case. So the controller will be providing the gate drive signals like we just saw into the digital inputs of the HIL, and then the HIL will be providing the analog outputs as feedback, which the controller would see in the real situation.
Yeah, so this is a completely fully defined system right now, in the sense that the processor is going to be running it's going to be running like it would in if it was running real hardware, and the Typhoon system is going to pretend to be the full system here. So we've got a somewhat more complex model the first time around here. So we'll get into what all these things are a little bit later on, but we're just going to run this in a very simple scenario right now. Let me just check which loads these are. 5 ohms.
Yeah, the other ones are 10.
And 10 and 10, so
yep.
Load 2, okay. So we'll compile this up, and we'll start running this load, this inverter, and then we can see there's faults in here, some heatsink temperature sources defined. When I'm generating the code of the ADC module, do I need to feed a fake signal for AD? Okay. So in PSIM, the question, this ADC block. So the ADC block, what PSIM knows to sample the ADC, or the generated code knows to sample the ADC when there's a signal connected to it. So if we think about this, if I draw here, if I draw a rectangle, so this is inside of the DSP, this chunk and this chunk. Everything in yellow is inside of the DSP. So we know that, so PSIM knows that this is inside the DSP, and then it also knows, because we defined a signal path from D0, D1, D2, it knows that it needs to define a get ADC statement for these. So that's where we see in this interrupt routine, where is it here? Get ADC 0, 1, and 2. It knows to do that, and only for those 3 signals, because there's something connected there. Now, when we're generating the code doesn't care. Like, it doesn't know that this is here. It doesn't know that this is here. All that's being converted into code is everything in yellow. So in order to, you can have a signal defined over here, and then and that's good, because we can run a simulation of this, like I did earlier. So we can simulate it if there's something there. If there isn't anything there, what's going to happen is we could simply just have, when you simulate it, it's not going to do anything productive. But when you generate the code, because you've got it wired up here, it's going to do that sampling for you. and the sampling rate defined here is at 10K. So that's being stuck. So 10K is running. So this interrupt routine is running at 10K, and I've got when we get into the protection stuff, I've got other interrupt routines running, other sampling rates defined on the ADC, and we'll see how that impacts things where these ADC elements pull into the interrupt routine. So there's lots of stuff going on here. That's a very good question. Would you please show us how you define the firing inputs three-phase inverter? So so right here.
Yep, just double click.
So we've got we've defined pins 1, 7, 2, 8, and 3, and 9. And the reason why we have those pins is timer 1. So the PWM outputs for timer 1 on this chip are the complementary pair maps to digital inputs 1 and 7 on the HIL. Timer 2 on the DSP maps to pins 2 and 8 on the Typhoon HIL. And timer 3, PWM timer 3 from the DSP maps to PWM or digital inputs 3 and 9 on the HIL. So that's why these are set up this way. And did this load in? I think it did. Oh, it's still compiling. What else can I mention here briefly?
The, the current signals actually are fed back. So you see the IA, IB, IC. So we define those digitals, but the current signals will actually be defined for feedback after it's compiled.
So once we're all loaded in, so I'll be able to probe and measure the analog signals over here when this thing is running as well. And what else can I mention here about this while we're waiting for this to finish compiling?
There we go.
And then, so there it went. And then, so we'll be able to look at the analog signals with my oscilloscope, and we'll also be able to monitor other signals as needed. But I've also got some further tricks up my sleeve with these SCI elements here. So we'll get into a lot of really fun stuff in a moment. Just as we're waiting for this model to finish loading in.
So this model looks like it's compiled at 500 nanoseconds. So that'll be our fixed time step running on the FPGA. So this model will be running on the FPGA at 500 nanoseconds. And the digital inputs, this is pretty important, are actually sampled at 20 nanoseconds. So this basically provides us enough Nyquist, so there's enough resolution to get about 10 bits resolution there.
Okay, so here's our setup. We've got 2 loads that we can swap between. We'll just run it with 1 load for now. There's all these faults that we can play with, but we'll get to those a little bit later. Did this load my settings? No.
No, you have to load the settings file. There you go.
There we go. So now I've got my load set up over here, and we'll just set these to their nominal values. And we can see I've got channel A's 1, 2, and 3 as our currents A, B, and C. And if we come back to PSIM, we can see that that's what we have here. We've got A, B, and C mapped into these 0 to hold elements here. And let me just check that what these are going to do. Okay, great. So we've got all of this set up here so that we've got 3 signals coming in, and we've mirrored that setup in with the Typhoon HIL setup. So what we're going to do now is start this thing running. And actually, I'm just going to change these quickly, just so we can understand the analog signaling here. So we'll start this guy running, and we'll pull up our waveforms. So there's our 3-phase sinusoid running. We'll also confirm that with the analog outputs here. So we'll take a peek at 2 of the waveforms. I only have 2 channels, so we can't look at all 3 at once. And let me just change the scale here to something big, and let me just take the offset off here. So there's 2 phases running in real time. Again, this is a real oscilloscope working, so we're watching these signals in real time here. So as I move things around, and so we've got our two signals there. We'll move that away, and we've got this working. And let me just minimize that away. Now I apologize. We're going to get into a lot of windows here really quickly. Where did the waveform viewer go? That's on this one. Okay. Slide that over, and then these SCI elements. These SCI elements allow us to connect to the DSP while it's working, and we're passing back over the serial communication interface. How can we properly use the SCI block in PSIM? So, so this is what this USB converter is doing here. So a lot of TI's boards actually can pass back the SCI over the JTAG connection, but on this particular board, because it's a little bit older, I need to access it with this RS-232 to USB converter. But a lot of TI's processors now, for example, like some of their newer stuff, like this sort of board, has that kind of communications built on, so you don't need this extra part here. But yeah, you need to make sure that that you can access the GPIO pins. In this case, it's GPIO pins 28 and 29, and so those are being mapped to this converter here. And then we're going to connect to COM port 3 because that's the one this is on. I know that already, but if you don't know, you'd have to go to your device manager window and check that out. And now we can look at the same 3 feedback signals, and we should be able to see the exact same 3 signals here running. So let me just check. So we've got 3 signals here, and we've got 3 signals over here. So we can see that these are for about 4 amps peak, 1, 2, 3, 3.5 amps peak over here. But we can see that on this side, that this is not set up. We're offset, as in if we look, let me just pause it. We've got 500 millivolts per division, so we're just under 1 volt peak here, and then we're over 2 volts peak on the negative side, so our offset isn't set up properly, and our scaling isn't matching what the DSP is giving us. So like in terms of real numbers. So what we're going to do now is, and this is the kind of the key, one of the key features here, is we're able to adjust on the fly the offset and the gain through these variables that I've set up. And this is critical, not just in terms of running against a real-time processor, but if in the case that you're running with real hardware and a real board, I'll pull back my little dev kit again. Like a board like this has current sensing circuits on it, and it could be, so this is an inverter setup. So it could be that the resistors are slightly off. It could be that the references are slightly off. There's lots of room for margins of error. And what this tool allows us to do is monitor these things directly after the ADC and to check to make sure that everything's talking the same language. So that's exactly what I'm going to do right now on channel A here.
And the nice part is, sorry, go ahead, Albert.
Yeah, I'm going to offset this in real time. I'm going to change these things in real time and get it to match phase A over here. Mm-hmm. And let me just change this so that it's on the scaling is auto, and we'll just get rid of these 2 signals here as well.
Once we set this up too, you only have to do this once, basically. Once your hardware scaling is kind of set up, you can save all these settings in Typhoon, you can save them in PSIM, and then you don't have to worry about it basically ever again unless you start seeing a little bit of drift.
Yeah. Okay, so what I'm going to do is we need to move this signal up a little bit. So we'll come over here and we'll go, we'll change phase A, and we'll just shift it up a little, maybe something like that. Oh, that was a little too much, maybe, and I know already that it's 525 is the magic number. So now we've got our signal properly offset from minus peak to positive peak. The next thing I'm going to do is we can see our signal over here is 0.92, and that is times 4, right? 1,
Yep.
2, 3, 4. And what's that math? 4 times 0.92, and because we're going to need this 4 times 0.92,
3.68.
3.68. So we're going to need to see 3.68 over here. So to check that, I'm going to change the offset here to 3.68, and we'll see that signal went away. And now what I'm going to do is I'm going to adjust the gain to increase it. So we'll adjust the gain in steps here. So 10 is too much. Maybe we'll try 3.45. Oh, there's the magic number. Obviously, I already knew beforehand what it was supposed to be. But yeah, so we had originally, it was a gain of 1. You know, we increased it a little bit, and we can see, and we can change it on the fly, this gain, so that we can get it to be correct. So we'll go 3.45, and we can see that that's now offset perfectly, and we can zoom in to see that we're touching the negative side is perfect. And let's check the positive half cycle as well by changing the offsets sign, and now we can see that that is perfectly touching there as well. And now let's go back out to full scale, and we can see now we've got a perfectly matching signal. Nice. from the HIL value. So the real values from what HIL is saying is the real values of what we're getting inside of PSIM. So this is real numbers. But so we've compensated for any current sensor divisions. We've compensated for any other numbers that would have been introduced into the system. So we've got apples to apples directly right now. And then we can double check the other ones. So IA, the other 2 channels, we did an auto scale there. So we'll just change everyone to talk the same language. And 2, so I already know that these need to be changed by the same amount. Thankfully, the HIL interface is equal for all of them. And I need to change the offset as well to 525. 525, and then let's grab the last one here, 1.525. And now we've got all the signals look really good. And if we just pause it here, we can see what's going on there. So there's our 3-phase sinusoidal signals now properly offset and also properly gained, so that we can do, 1 amp over in the real world will equal 1 amp inside of the DSP. Now the next thing that I've got set up here is we can double check to see what's going on here a little bit. So I've got access to IQ and ID, so I can actually change in open loop the IQ reference. Let's make it smaller, and we can see everything. Oh, this auto scale is really quick, so you can actually see. Let me just take this off of, put these back on, and put this back on 1. Okay, so I'll play with IQ. So I'm changing IQ on the fly here, so we can change it back up to where it was, make it small again, 0.1. So we can change all these signals. The auto scale is making it maybe a little difficult to see what's happening. Yeah, we can see on the left-hand side all these signals are bouncing around. I can also have access to the frequency. So there's 10 hertz, and then there's 100 hertz. So I can change these numbers on the fly as well. These are all numbers that are accessed over the serial communication interface. So it makes it really easy for me to check things and confirm things and play with things during runtime instead of pre-compiling all the time. There's a question from Osam. Ryan, do you want to? Oh, his hand's been raised for 120 minutes so far.
I'm not seeing that question.
Osam, did you have a question? I've unmuted you.
Yes, I was asking if everything we are doing here can be made with HIL 402.
Yes. Yeah, the HIL 402, the only difference, well, actually, Ryan's probably better to answer that question, but Ryan,
yeah, so
can everything be done?
It can. The 402 is basically a newer version of what Albert has. Albert has a 600 series, but there's also the 400. But yes, this can be run on 402, and actually this can be run on 602 as well. So.
Yeah, fine.
Mm-hmm.
Okay, there's another question I saw. Someone had their hand up. Where was it? Okay, no, it went away. Okay. where are we here now? Okay, so we've got all this working in open loop, and we'll step away from the code generation side of things now and look at how we can do controller design for this. So let me just disconnect this and shut that down.
The
I'll leave the
on
inverter.
the analogs, did we touch that part as well?
The scaling on the analogs. Well, we just did that.
Yeah, yeah.
On the hill side. Well,
because you set
yeah,
those
we
to
could.
1, I think.
Yeah. So these are set up over here to 1. So essentially, the scaling we just did on the PSIM with the DSP scope, that was we could have done similar scaling by playing with these numbers as well. It's either or. Once you have them set up on one system, you don't touch them on either side, if that makes sense. So this is set up on, so we're running with these parameters, and we've got the appropriate PSIM coefficients defined for when we do it on, we've got the appropriate PSIM coefficients defined over here for when we're running the processor. So as long as we're consistent of where we change the gains and offsets, we'll be okay. So yeah, we don't really need to worry too much on this side. But I think these were originally 10, right? So this was a different this was a different setup that I had before. The ADC process is run inside the DSP. Yes, the analog to digital conversion is happening with the TI's ADC. If you wanted to run an external ADC, that is possible with PSIM. PSIM has the ability to set up an SPI interface if you want to run an external ADC conversion. If Chris has comments about the accuracy of the ADC on this, then now would be a good time to mention them. But how can the PWM outputs be ported to HIL inside the hardware config in PSIM? I'm not sure I understand that.
Yeah, I don't.
Ryan, do you see the next question?
Yeah. Could you clarify a little bit how the PWM outputs could be ported to the HIL? Because currently the DSP is providing the PWM outputs to the digital inputs of the HIL. So the HIL is sampling those digital signals and basically providing or switching the gates as needed. If that makes
Yeah, there's let me just I'll just actually, I've got a table here in my big Word document. So let me just minimize this here. Cancel. Okay. Okay, so I think what you're referring to, so this is the tutorial document that I've been working on that covers all of this in great detail. But I think what you're referring to is this setup here. So GPIOs like EPLM 1A and 2A are mapped through the interface card to pins 1 and 2, and then we need to change that over here to SA top and SB bottom. So does this make sense? So PWMs 1A and 2A are mapped to D1 and 2, so we have to use those. There's no, oh, I'd like to map it to pins 3 and 4. No, we have to use 1A, 2A, 1A, 2A, 3A, 4A, 5A, and 6A, or, right, so the complementary pairs are 1A and 1B, 2A and 2B, 3A and 3B. So there's no wiggling about that. Okay, so moving to the closed loop end of things. So in PSIM now, what I'm going to do is I'm going to run an AC sweep. So an AC sweep in PSIM is very handy. It basically introduces a perturbation into your reference or into any reference that you want, and we can measure the frequency response at any point in the system. So in this case, in this case, we're introducing a perturbation into our open loop IQ reference, and we're monitoring the feedback IQ over here, and we've introduced digital sampling elements and digital delay elements so that we accurately model digital delay properly. And so we're going to be designing directly in the Z domain. So this sweep that I've got here, we're going to go from 10 hertz to 4 kilohertz. And again, so that's driving into this IQ reference. And then this AC probe here on the feedback point is going to compare the phase and gain versus the perturbation amplitude phase and gain, and the perturbation amplitude phase and amplitude. And the nice thing is that the switches are still in circuit. So the PSIM AC sweep considers the switching nonlinearities. There's no average modeling that we had to do. It's very easy to introduce these very quickly. So we'll run this sweep and we'll get our open loop plant response. And so here's the open loop plant response. So we can see we have a gain of about 20 dB at low frequencies, and then we start rolling at about 100 hertz. And rolling down here, hang on a second here, my Slack program here is starting to annoy me. And then our phase, we can see the phase here as well. So the phase is starting to roll off, and then we can really see that it dives down towards, a very strong lag as we get higher in frequencies. And this is the impact of digital delay. So if this was an analog system, we'd probably transition and then hold steady at about 180 degrees or 90 degrees. I forget exactly what the analog sweep looks like on these, but and with digital, it just keeps rolling on forever. So this is very important when we're designing the controllers for this. And so from this tool, these AC sweeps, we import these into another tool called Smart Control, which is this program here. So this green line is the open loop plant. And so what Smart Control does is we define that we want to do a PI controller, and the denominator, the transfer function ID IQ ref. So I've not done the math on so the sweep. I think I know what you're asking. The sweep response. So this is IQ perturbation versus IQ feedback. So this is IQ. So this is introducing a perturbation in IQ and observing the resulting perturbation. So IQ versus IQ. We could look at coupling as well if we wanted to. IQ perturbing IQ and looking at ID, and perturbing ID and looking at IQ. So all of those, the interchangeability is considered, but in this particular instance, I'm treating ID and IQ as separate control signals. So Smart Control, we're importing that plant as a frequency response. We're defining a simple current sensor with just a simple gain. And then we've also got a PI controller defined here as well. I won't get too much into this, but essentially we get to, where did that map go? Essentially we get to play around with our solution space, and we can see our control to output transfer function changing the pink line here. So we want to see a nice DC gain at low frequencies, and then we want to see nice attenuation of our switching. And then this plot here gives us an approximation of what we would see for the step response. And so we can zip around in here and see and try and find a stable solution. Thankfully, I've already found a good solution, and that has been implemented in the closed loop forms. So this is the closed loop controllers that I've come up with. So in Smart Control, this panel here, we see we got a cross frequency and a phase margin, and S-domain coefficients that define that. What we've done in PSIM is we've implemented those S-domain coefficients with a Z-domain, a digital domain block. So this block takes S-domain coefficients and then converts them to, or discretizes them with backwards Euler. And so those S-domain coefficients are now defined as Z-domain coefficients, which I have here. We've got a sampling rate of 10K. And what we can do in this particular simulation is look at the loop gain. So we can simulate the loop gain here. So I think for this one, I had done a cross frequency of 500 hertz and phase margin of 50 or something. And we can measure and look and find the cross frequency, which is right here. So that is right at 500 hertz. and our phase margin is 180 minus 130, which is about 50. And we can see the phase rolling off here. This jump up is a result of the phase rolling over from 360 degrees, and we can see our amplitude response here as well. Okay, so that's if you. I know that PSIM in this case, if you prefer for HIL, they are more or less of what we are managing your calculated in a Simulink and DSpace as controller prototype and HIL is a real-time inverter. What is this right? I don't know. I've never used a DSpace tool. If DSpace can take the place of the HIL platform, potentially. The nice thing with the Typhoon HIL setup is it has this interface card for the TI MCUs already defined. So all we need to do is take the MCU that we want to use, download the code to it, and run it against the hardware and loop setup. I don't know what DSpace has in that regard.
Yeah,
Ryan, do you have any comments?
DSpace has the Microlab box for RCP as their newer version, but they also provide some HIL solutions as well. But obviously, we're going to be a little bit more biased towards our own things as well. But one good thing to note is that the Typhoon simulator with the TI interface card, with PSIM code gen, this is all designed for power electronics. So this is running on the FPGA faster than any other product on the market right now. So you'll basically get the speeds that you need for inverter signals, and you'll get very high fidelity using the Typhoon platform.
Yeah. I know that Simulink has cogeneration tools, and I've never used their cogeneration tools, but I've heard from a number of people now that the Simulink cogen stuff is cumbersome to use. I've had several clients now recently who have bought full MATLAB cogen setups only to phone me up to buy PSIM cogen setups because they found it almost unusable. So the nice thing with
go ahead.
I was going to say the thing with PSIM is we're defining a project that runs standalone. So this control card, yes, it's running against a hardware loop simulation right now, but that's running real time. We could just as well, if we had set the protections up properly, we could run it, take this control card and slot it into this control card and run this inverter just as easily as we are right now. The control code, it doesn't care where it's going. It's nice to run it in hardware and loop because we're not going to blow anything up if there's any errors that we discover. So this control code, once we have this fully defined and we know that it's working properly, we can just take this and plug it into the real thing right away. There's no intermediary steps, and I'm not sure how that all can be accomplished with those other tools.
Got another question as well.
Do we need to have hardware config block and PSIM to check ADCs? No. So as long as you're using standard the default ADC parameters or PWM parameters or digital I/O parameters, we don't need the PSIM hardware configuration block. So the element he's referring to, which I don't have in any of my simulations, is this hardware configuration block. So this block is only needed if you want to define something slightly slightly beyond out of normal. So in this case, like the ADC pins can only be those particular pins. The PWM pins that we're using are only PWM 1A, 1B, 2A, 2B, 3A, 3B only come on their respective pairs. We can't map them somewhere else. So we don't need the hardware config block or anything to do with it as if we have everything set up with the default values here. Okay, so moving along to closed loop. So
onto the fun stuff.
Yeah, onto the fun stuff here. Closed loop. Here we go. So this is now I've got this set up. I've got a bunch of gain settings set up. I haven't done the math to make sure that everything talks to each other in the same language. So I have a set of parameters that get used. So I've used conditional logic. So I have a set of parameters that get used when we do generation or versus simulation. And so I am going to set this up to run in simulation right now, and I've got my closed loop control defined here, so we can just run this, and we're going to be able to see, let's pull up a runtime graph window, watch these things go.
Can you paint which portions are going to be code generated as well?
Yeah, I'll draw the same blocks again here. So edit, so draw a rectangle. So again, all of this is cogen. So all of that gets turned into C code. And we can basically, the easy way to think about it is we need to define an input point to the DSP and an output point to the DSP. So we have inputs to the DSP in the forms of ADCs, and we've got outputs from the DSP in the form of PWMs. Everything in the middle turns into C code. And we can pull up, so A, B, and C. So those are there. We can look at ID and IQ. IQ versus the reference is there. And we can also pull up ID feedback. So ID is going to be held at 0, which it is. IQ, a little bit overshoot, and then it settles out. And so we can also see that these signals have been discretized. And then we're also looking at the real-time signals up here. So these are the continuous time domain signals, and these are the discrete time domain signals. So IQ versus the feedback. So we've got a little bit overshoot, and then settling out nicely. I have a problem with the PSI's window. Every time I am trying to use it, a message pops up saying it's not part of the code generation. Please, if you have questions about elements that don't work, or you have questions regarding PSIM use, please send me an email and we'll talk about those over email. So my email is a.dunford@powersimtech.com. So any kind of troubleshooting questions that you have about your own simulations, please send me an email and we'll talk about those offline. Okay, so we'll generate the code for this. Again, I need to change my little code flag here so that we use the right gain settings. Save, and then simulate, generate code. And now again, we'll do the same process here. We'll import this into CCS. So I'll just close this project, and we'll do a new import project, import legacy project, browse, and we want close loop, open, next, finish. So, you know, I haven't done any other, make this the active project. I haven't done any other setups in the background. The only thing I need to define is a target configuration so I can talk to the processor properly. And you can see I've got a library of other processors we support here as well. So the 035 and the 069, and again with other various JTAG communication protocols. And so I can just start debugging this again. So that's now loading onto the DSP or to the MCU. And we'll start this running again, and we'll come back to Typhoon, start this guy again, and we should see our, oh, did those open on a different, oh, they're over here. Sorry, I've got lots of, so here's our signals again. So again, we can stop that, start that, they're back up again. If I pause the processor, these go away. Start the processor back up again. They're working. Let me just do some window management here. Move that over. I have 2 PWMs in my circuit in PSIM. How can I put them in order so HIL can use them correctly? That question is answered by this. So if you have PWMs defined in PSIM, you're going to define them, assign them to a PWM timer, and then you're going to define, those are going to set which digital inputs you're going to use. And then you define, so this is the 3-phase, this is the control block for the power elements in the HIL, so you're going to define which, so we got PWM 1A is on 1, and 1B is on 7, so 1 and 7.
Yep, that's assuming you're using the TI DSP board, because that will map those signals.
Yeah. Yeah, so this is dependent on the interface board. What else can I talk with here? Right, we're in closed loop now. So let me make a little bit of room here. Okay, so we've got the Typhoon stuff right there. We'll pull PSIM back up. Frequency characteristics, I'm going to close that. We'll close that. AC sweep, we'll close that.
So we've kind of walked through all the, I guess, the setup phase, and that was kind of a lot of material.
Yeah.
But once you kind of have it set up and running, this is kind of the point where you can go in and really start testing and tuning your controls and doing some real iterations to your code and generate changes quickly. So this is kind of, we want to take this time to show you, now that we have the setup good, or the setup is good, we can basically go in, start doing some faults, start doing some like over voltage and things like that, see how their control responds, and make small changes to our code and see how quickly we can actually make those changes and improve our code.
Yeah, yeah. So again, we're running closed loop here. At least I think we're running closed loop. Yeah, let me just pull up IQ. So IQ, so this is the IQ feedback value. Again, whenever there's a signal we want to look at, all we need to do is come in here and put one of these SCI blocks down, and then we can map it back and pick it up in the scope here. So here's the IQ reference value. So as I move IQ around, oh, this is the wrong load. Let me just switch loads. We want to come into the contactors.
Yep.
So we've got so we've set up a lot of stuff here to kind of do some demonstrations. So one of these things is swapping the load around. So we've got two loads defined, load 1 and load 2. So, and those are controlled with this contactor state. So what we can see in PSIM is, and let me, again, lots of windows here, and signals. Let's push these up a little bit here, maybe 2 per scale. And I apologize that there's lots of windows, but I mean, it's the nature of the beast when you've got all these different programs here. So we've got IQ feedback right now. It's set up at 8 here, and we can change this around. So we push it down to 5, and we can see that we're getting good control here. If we go really small, we can see that we're starting to get deformity in the control signals, and we can increase the current again. We can also see what happens if we change the if we toggle the load again. So we put our other load on, we can see that the IQ, we're asking for a reference of 8, but now we're at 5. And that's because we don't have enough DC bus now. We don't have enough, we can't actually control, we've saturated the controllers. So our modulation waveform is probably at plus minus 1, which is our limits. So we would need to actually, in order to get this to control more, we would need to change our sources and give ourselves a little bit more voltage here. So give ourselves a little bit more voltage, and we can then come back and look at see if what the IQ feedback is doing, and we're back in business. So this is our basic closed loop form, and we've also got some other things that we can do here. We've got a fault set up, so we can trigger a fault, and we can see what happens.
Yeah,
and we can see that it's a pretty bad scene. So maybe we should start playing around with it. There's a lot of questions coming in, Ryan.
Yep.
What was the first one there?
So
I was wondering.
Yeah, I was wondering what generates the hardware emulation code VHDL-C for RTDS HIL, such as the inverter and machine. Is it produced by PSIM or something else? Otherwise, could you provide an example on how source code might be employed so that the entire ACD does not affect the entirety of the source code, such as safety applications? So,
What generates the hardware emulation code? So the hardware emulation code is generated by the Typhoon HIL program. So Typhoon is a standalone tool that generates the code that runs the real-time portion of that.
And that's just for the plant simulation. So that's not the code generation for the embedded processor, but for the plant. But that's all built into the Typhoon software. So you kind of similar to like Simulink or other environments. It's library on the left. You saw earlier when Albert compiled the model. You basically can build up your model, drag drop, compile it with one click, and it'll be built into or put onto an FPGA within a couple minutes. We're compiling to a soft core, so you don't have to wait the full hours amounts to get that thing compiled. But it's all built into the Typhoon unit.
Thomas has a question. Yes, the plant model is running on the FPGA. The DSP is running. The program that we've compiled from the DSP is from Code Composer Studio is running on the DSP. And what's that other question there from Khalil? For the current feedback in Typhoon HIL, it is sufficient to respect the order's name of the current lines in order to connect them to my DSP card. Or I have to do some. Yeah. So the feedback settings, all you have to do is define, which signal you want to map back on which channel. So there's 16 channels, so you can map back 16 signals.
Yep. And you can change that. Scaling, the offset, etc.
Referring to having power electronics, it says prefer play. Can the three-phase inverter nonlinearities due to dead time propagation delay of signals and finite switching time of real devices be analyzed and perfectly compensated? So the kinds of questions you're asking there, if everyone can see what Assam's question is, so that's nonlinearities with regards to propagation delay and finite switching time, and dead time. So with dead time, you can observe the effects of dead time in these simulations, as long as the dead time resolution, like this 4 microseconds here, is big enough to be sampled by the HIL system.
Exactly.
So that is your limit there. So otherwise, it'll be unobserved. The other things you're talking about, those nonlinearities, those are not possible to be simulated in real time. Those add a huge amount of computational effort. So nonlinearities for switch delay and like real devices turning on and off, this is not possible to be done in real time. You can run those models in PSIM. We do have nonlinear models in PSIM and characteristic models, but those simulations require a very small time step and will take and take time to run. So it's all a question of what you're looking to understand. With what we're talking about here, we're trying to we're showing methodology for control design and overall system design and controls. The kinds of questions you have, those are very detailed simulations and are not what would be covered by this sort of prototyping. The impacts of them could be introduced, but you would have to understand what they are and then introduce them in such a way that it can be handled. But you could look at that in an offline simulation only mode. I hope that answers the question.
Back in. One more.
Okay. Yeah. Let's hold on questions for a moment here. Just let me finish something.
We'll do questions here in about 10 minutes. We need to wrap up the remaining of the demo, and then we'll jump into questions.
Okay, so I've got I've implemented now a simulation that has some protections involved. So again, I'm now detecting an over or an under voltage DC bus, and I'm also doing a simple overcurrent check, and I'm feeding back a heatsink temperature. And so what happens here is on the DC bus settings here, I'm turning off the PWM. So if the DC bus is within range, we run the PWM. If it's out of range, we're not good. If IQ feedback is too big, we're going to turn off the PWMs. And then if the heatsink is too hot, I'm going to scale IQ. And this is just really simple really simple stuff. So the IQ scaling is if the temperature is over 110 Celsius, I'm going to scale the IQ reference value by 75%. So nothing too sophisticated, just to kind of give you an idea of how all this kind of stuff works. So again, I think I just generated the code for this, code protections, and we'll come over here and reload this into CCS. I'm losing all my windows now. There it is, behind everything. So we'll stop this, and we'll actually, let me just turn off this fault state on the contactor. Great. Sorry again for all the windows. Okay, so we'll import the new project. We'll close the project. Project, import legacy project, come to browse, app note with protections, open up, next, finish. Okay, and we'll run this one now. Okay, so some of the protections that I have implemented here are over voltage, under voltage. So the first, let's check to see what happens if we have too small of a DC bus or too big of a DC bus. So this is running. Let me just shut some of these things down.
Yeah, that's Windows. Back to the control center.
Yeah.
You can close that output settings. You don't need those anymore.
Right, thanks. I'll close this one.
One thing you'll notice on the Typhoon there, the DTV, that's a dead time violation. So if the controller ever has a state where basically there's two shorts, it will throw that dead time violation. So that's a nice helpful tool. But you can clear that just by right-clicking and clearing the flag.
Yeah. Okay. Reset flag. And is this working? It is. What's the sources here? Okay, 120 volts. Okay, so we were already in an off state, so let me reset this flag. So our DC bus is set to, let me just move these things around a little bit. So our DC bus is 120 volts. So I had set in the PSIM, okay, if we're too low to shut down, so 80 volts, we're off. And if we're too high, 160 volts, we should be off as well. But if we're at 125, we should be working, and we are. So that over voltage stuff is working properly. The next thing we're going to play with is doing some faults. So let's fault this thing, line A to B. We've got fault currents here, and we can see I actually had set up some overcurrent protection, but it's not working. And I don't have time to show you exactly in the offline simulation why it's not working. But what happens is it's sensing the fault, it's stopping the PWM, but then it starts up again once the fault clears. So we actually need to add in a latch to this, which I hopefully have down here. And so we'll introduce a latch to this system so that we can latch the current off. And we'll come over here and add this in right here. And I've also got a reset defined as well so we can clear the fault. And so we'll just go simulate and then generate the code again.
Mm-hmm.
And we'll go back to CCS and we'll come over here, we'll pause, stop, and then we'll just build again. And let's leave that off. So we've got our currents flowing around. Let me just close this window. And we need to run this up. Okay, so that's working. So this is, we've got our currents. Let me just clear this flag. And then we will close this. And we can see that our fault currents are off. So that fault exists. Ryan, how do I set it up so that it's we can
you can do a trigger?
to do a trigger so we can see just let me clear the fault. So I set a reset for us. So let me just clear this fault, and I'll pull back up in PSIM here, simulate the tool, DSP scope.
Yeah, you can do the trigger in the Typhoon side as well.
Yeah, I just need to reset the flag.
Gotcha.
So there's our signals are back.
Mm-hmm.
So their signals are back. This guy's back. And so how do you do the trigger? It's
you'll see on the left side you got your scope, so you want to switch that to capture.
Yep. Scope and go to capture.
Yep. And then hit that little cog with the green arrow.
Yep.
This is going to import your settings from scope to capture. And now just go ahead and set up your trigger. So on the right hand side, the top
These guys here?
Top right arrow with the cog. So this is your trigger. So you want to basically say, hey, that's fine. Define your threshold.
Okay, we'll do an overcurrent, so we'll do quite a bit, and then we should pick it up. And then, so let's
hit the T with the little arrow, and that will start your trigger. Yep. So now
let's put a false in. Oh, we didn't get enough on the back end, but it looks like the signals are off now. So yeah, I think hopefully you guys kind of get the idea of what we're getting at here for all these things. Let me go back to the scope. Oh, that didn't latch for us. Oh, it's because I didn't clear this. Okay, let's try that again. Capture. Oh, there we go.
You'll have to set the trigger again.
Yeah, scope. And then let me just reset this. Oh, and I'll need to turn the contactor off.
Yeah.
Okay. Anyways, I think now is a good time for questions. And bear in mind, we've got Chris online. I think he's probably, hopefully he hasn't got he's still with us, but he's online to talk about the processor as well. Chris, I don't know if there's anything that you want to talk about with regards to TI processors right now and why they're an ideal choice for power electronics control, but now would be a good time to chip in a couple marketing points there.
Yeah, this is Chris Clearman from TI. Thanks a lot, Albert. I would suspect that many of the people on the call, especially if they're already using your tool, which from the comments, it seems like many of them are, probably are already familiar with C2000. But C2000 is a processor platform from Texas Instruments. It's a 32-bit real-time controller, which is essentially a DSP and microcontroller type of functionality combined into one. And there's several different processor families within C2000. Most of the products that would be supported by Typhoon, most of the customers are using Delfino, which are higher-end versions of the C2000 with the most processing capability, largest amount of memory, largest amount of peripherals, larger packages. We also have a Piccolo family, which is more of an entry line, lower cost, smaller memory configurations, smaller processing capability. But these are pretty much the de facto standard processors in the market for power electronics control. You'll see them used not only in education but in industry. And we've had a pretty dominant space in this position for all sorts of power conversion applications in industrial, automotive, etc. So the product they use today, the F28335, is part of our Delfino family. We actually have a follow-up part to that that went into production last year with a different part number, F28337X series, and the superset part is the F28379D, which actually has dual instantiations of the CPU core along with new accelerators, our parallel coprocessor called the CLA, double the memory, new peripherals, etc. So that part is also being supported, I'm sure, by Typhoon, and is pretty much the part that new applications are moving towards to get the best and latest and greatest of everything from C2000. But the F28335 that was shown here is kind of the flagship part that's been in production. It's used by thousands of customers, and it has a very long lifetime. So if you are using that part, no problem. And you can go to ti.com/C2000 for more information on our parts, and we of course have a E2E community where you can ask questions and we'll get you your answers.
Thanks, Chris.
Great.
And yeah, so are there, open up to the floor now, I guess, for questions. There have been a lot of questions over the course of the webinar. Hopefully we've gotten to them all. There was one that was getting into motor.
Yeah, the motor control. How would that be mapped to the HIL? So you would basically use the same, if you're using the same processor board, you would just look at the inputs and outputs of the HIL, and you would also look at the inputs and outputs of the processor and map them together, if that makes sense. It'd be very similar to how it was mapped for the gate drive signals for the inverter, but you're going to have different signals.
Yeah, it's just different signals. You know, in this particular example, we have, you know, an inverter with elements here, with the current feedback elements. If we were going to have a motor set up, then instead of having this load here, we would have one of like the PMSM motors. And then if we were doing sensor control, then we would feedback the shaft. If we were doing sensorless, we would put in a sensorless algorithm. And actually, that's a nice segue to some of the other advanced functionalities. PSIM has recently rolled out InstaSpin support for the F28069, so you can do code generation around the very easy to use InstaSpin platform, and very powerful sensorless control observer from Texas Instruments. And then there's a question, I want HIL to put yes, and you can define a mechanical load in with the hardware and loop system as well.
Exactly.
So all that can be handled. Any further questions?
And again, this all this content will be recorded, and we'll put it up on the web here in the coming weeks, as well as the full guide and tutorial to kind of go through and recreate this yourself. Good?
Okay, well, 30 seconds. Yeah, everyone gets 30 seconds to think of more questions, or we'll close it. Or we'll close
No
it
more
down.
questions after that.
Does PSIM launch? Yes. PSIM could. No, sorry. The latest Delfino processor that Chris was talking about, that is scheduled for release for PSIM for support after a F20. There's a new processor coming online in the summer, Chris. I forget the number. It's a Piccolo variant. We're supporting that one first, and then we're rolling out support for the F2837 series. So the support for the F2837 series will likely be closer towards fall, winter, as we're supporting the latest Piccolo variant. Chris, I don't know if you're still on. I forget the part number off the top of my head. What's that new Piccolo line that we're supporting? Do you know which one it is that we're supporting right off the bat?
There's a new Piccolo product that we're sampling now, and we'll start production at the very end of this year. It's a Piccolo F28004X. There's a superset part F28049M that is available. It's kind of a product folder with data sheet, and that part is a new series that will roll out, kind of a reboot of Piccolo, a high-performance Piccolo device with quite a lot of new features on it, especially for power conversion applications.
Yeah, that's the one we're supporting. We're rolling out support for that, and I think our work on that will be done by summer, hopefully, and then the 2837 support will come after that quite quickly. But I think, Chris, the 37 is pretty much pin compatible in most instances with the 335.
No, it's certainly not pin compatible, and there's quite a bit of performance features that are added. The 379, this family is, I would say, peripheral compatible to our new Piccolo part, though. The new Piccolo part is based on this new high-performance 379 series.
Okay. Yeah, I think there's a little bit of reading I need to do to catch up on all your stuff. But yeah, that's the development plan from PSIM's end. I guess that resets our 30-second timer for questions. Anyone?
All right. I think we're good to go.
Okay. My email, I put it into the chat a little earlier. I think you all have Ryan's email as well.
I'll put
And
that in the chat as well.
I think the best way to get a hold of Chris is to log on to the E2E forums on TI's website. I think you're pretty active on those E2E forums when it comes to answering questions that people have with regard to the processors.
Of course.
Great. Okay, guys. That's it from us, and thank you so much. And we'll post again. I think the next webinar we're going to be doing is going to be on grid-link inverters, and we'll probably use a Piccolo processor in that instance, so you can have a better view of the various processors that you can use with the cogeneration platform. And then we'll get into the grid-link inverter stuff and microgrids with the next presentation. Okay.
Thank you guys very much. Have a good rest of your day.
And look for the content package to be released soon. The tutorial that covers all of this will be comprehensive. I'm up to about 40 pages right now, and I was hoping to be done by now, but it's becoming very thorough. So have a look for that when it's released, and it should go over all of this. And again, you'll have access to the recording here to go over everything as well on your spare time.
Cool. Thanks, you guys.
Thanks. Thank you.